So in this lecture, we're going to be talking about covalent compounds. So again, covalent compounds is when you have two or more nonmetals joined together to form a compound. Again, recall that hydrogen in this case is a nonmetal. So any of the blue things in this periodic table joined together equals a covalent compound. So how do we name covalent compounds? So the way that we name covalent compounds is actually quite straightforward because we have this thing called prefixes. Okay, mono means one, di means two, tri means three, so on and so forth. So in this case, one of the things is we just count, we just indicate the number of atoms by using this prefix system. Right? FYI, we do not use mono for the first atom. The first atom, if there's only one of it, never gets the mono. Okay, so let's look at an example here: carbon monoxide, CO. There's one carbon, there's one oxygen. Again, we don't use mono for the first atom, so therefore this is just carbon, and since there's only one oxygen, this is monoxide, carbon monoxide. Here we have two nitrogens and five oxygens, so therefore this is going to be called dinitrogen for 2 and pentoxide for 5. Going the other way, writing formulas is straightforward because again we have the prefix system, right? So if I tell you carbon tetrachloride, carbon with no prefix means there's only one carbon, and tetra means 4, so that means there's 4 chlorine. So all we do is we write C followed by Cl4. Okay, so again, a very important thing is you always write the first element first. So here we go. We have diphosphorus octoxide. Well, di means there's 2 phosphorus. Octa means there's 8 oxygen. So this is P2O8. All right. So naming formulas for covalent compounds should be the easiest thing ever. There are acids. That's a complicated naming, but we're going to be covering that naming system when we cover acids at the tail end of the semester. Okay. Now, before we have covered how metals and nonmetals, when they combine to form ionic compounds, fulfill the octet rule. Now, for nonmetals, this is not the case because nonmetals like to gain electrons. Well, what happens when you have two, in this case, two nonmetals, who both wishes to have electrons? Well, no one's going to win, right? So again, so this is where Lewis structures come from. In the Lewis structure, we indicate the number of valence electrons by dots. So helium has 2 valence electrons, 2 dots. Krypton all the way to radon has 8 valence electrons again, 3s2, 3p6, 4s2, 4p6, so on and so forth. 8 dots around it. This again is the preferred electron configuration for all elements, because that indicates that they're highly stable. Okay, so how do nonmetals do this? Now obviously nonmetals, both of them wish to gain electrons. No nonmetal wishes to lose electrons in this case. Okay, so here we have 2 fluorine molecules. So when F2, this is actually the difluoride atom here, what happens when they join together? Well, as you can see, fluorine has 7 valence electrons, both of them. Now again, they want to have 8. So how does 2 fluorine atoms fulfill this octet rule? Well, look at this, folks. If they share 2 electrons, I want you to count how many electrons is around each fluorine now. Individually now, along with their 7 valence electrons with the sharing electrons, they each now have 8. So by sharing electrons, nonmetals fulfill the octet rule. A very important caveat to this one is since in nonmetals, and since in covalent bonding, no electrons is lost or gained, the whole compound most of the time is considered neutral. Here are a few more examples of covalent compounds. Oxygen here, if you can see it clearly, folks, they're just not sharing 1 electron each, they're sharing 2 electrons each. This is actually called a double bond. And again, if you imagine your mind counting electrons, 1, 2, 3, 4, 5, 6, 7, 8, this oxygen has 8. This oxygen also has 8 because again, they are sharing this 4. This 4 means it belongs to both of them. Okay, so that's a double bond. Nitrogen, folks, is triple bonded. They're sharing 3 electrons each, so each nitrogen is sharing 3 to the other nitrogen. And again, if you count, they're sharing 6 plus the other 2 electrons. Guess how many they have? 8. You should see a general trend right now. So if a nonmetal needs to gain 2 electrons, it normally will have 2 bonds, okay? And FY, it doesn't have to be bonded to the same thing. It could be bonded to different atoms. Look at carbon here. Carbon is in group 14. It has 4 valence electrons, therefore it wishes to gain 4. How does it accomplish that? It is bonded to 4 hydrogen atoms. So in this case, again, 2, 4, 6, 8. So now this carbon in the middle now has 8 electrons, so it has fulfilled the octet rule. Now, why does hydrogen only have 2? Well, folks, hydrogen is group 1, which means it's the same group as helium. Helium only can have a maximum of 2 electrons, so in this case, hydrogen is also fulfilled its duet rule in this case. Okay, so there are exceptions to the octet rule. One of the exceptions is there are some covalent compounds that do not fulfill the octet rule. Boron is one of them. Boron, I don't know if you know, this is in group, like it only has 3 valence electrons. So if it bonds 3 times with 3 different elements, again, the key here is you cannot bond with someone unless you share an electron. Okay, there are exceptions to this rule. I'm generalizing here, but in this case, let's just keep this the way it is. Okay, so in this case, since boron only has 3 electrons, that means it can only bond with 3 other atoms, which means to say it can only have a maximum of 6 electrons. And then something that will blow your mind is period 3. Period 3 means HERO 3. Period 3 and higher nonmetals can have more than 8, hypothetically can have more than 8 electrons. Okay, and the reason why that is you have to understand that in the 3rd energy level and higher, there's actually a D block. And the D block, if you recall, can actually contain up to 10 electrons. So hypothetically speaking, group 3 and higher nonmetals can actually have 18 electrons. Okay, I'm not going to confuse you because there's actually can go higher than that. Just by looking at this phosphorus molecule here, this phosphorus atom, each of these lines is a bond. So that means 2, 4, 6, 8, 10. Phosphorus in this case has, actually has 10 electrons. So it has exceeded the octet rule. But just remember, that's just period 3 and higher. Okay, so I am gonna do some Lewis structures again. So what I want you to do is I want you to like recall this one. So the way that you actually do Lewis structures and trying to fulfill the octet rule is somewhat complicated and sometimes not. Okay, so I am gonna do an example. So let's do a Lewis structure for, in this case, carbon disulfide. Okay, so carbon, FYI, the first element on your case is always going to be the atom in the middle. Okay, there's going to be exception. I'm going to let you know. The other thing that you can think about is group 13, 14, and 15 normally are also going to be in the middle. Okay, so boron, nitrogen, okay, oxygen, sulfur, so on and so forth. Okay, so in this case, you always make sure that you draw each individual atoms with all of their valence electrons. Sulfur is in group 16 in this case, so therefore it has 6 valence electrons. So 6 here, 6 here. Carbon is in group 14, it has 4 valence electrons. So you draw them out first, and what you do is you make sure that there is one, at least you start by bonding 1 electron each. And then what you do is you count, and so for this sulfur, it still has the 6 valence electrons, but now it's sharing 1 more from carbon, so therefore it now has 7 valence electrons. This sulfur is the same, 7. This carbon, if you count, has 1, 2, 3, 4, 5, 6. So as you can see, the octet rule in this case is not satisfied. So how do you deal with this? So the way you do this is you are going to move, in this case, 2 other electrons in the middle. So you're going to do this way. And we are actually also going to move 1 electron each from each of those sulfur. We're going to put them in the middle, and guess what we're going to do, folks? we are going to bond them into double bonds. And you are going to keep doing this until you get the octet rule. So now let's count the sulfur. Now this sulfur still has the 6 valence electrons, but now it's bonded with 2 other electrons. So therefore, guess how many it has? 8. That's the same with this. And guess what happened to carbon? Carbon now has 1, 2, 3, 4, 5, 6, 7, 8 as well. So now all of them now have fulfilled the octet rule. So this is the actual structure of carbon disulfide in Lewis structure. So here we have another example. In this case, this is the actual nitrite ion in this case. So there's 1 nitrogen and 2 oxygens. Here in this case, there's a -1 charge, which means there's an extra electron hanging around somewhere. Okay. So one of the things is we need to, first of all, add that electron right away to one of these 3 atoms. And the way you decide which atom gets that electron is by looking at their electronegativity. And this electronegativity numbers come from page 3 of your exam reference sheet. So nitrogen has an electronegativity of 3.0, oxygen has an electronegativity of 3.5. So therefore, that extra electron gets added to, it doesn't really matter, one of these oxygens. Okay? So and then we proceed again with bonding. So again, nitrogen has 5 valence electrons. Normally oxygen has 6 valence electrons, but in this case we have 1 oxygen that has 7 because again of an extra electron. Then guess what we do? We bond them again. And what we're going to do is we're going to count. If we do that, we can now see that this oxygen now has fulfilled the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. All right. This oxygen, however, is not, because it has 1, 2, 3, 4, 5, 6, 7. And this nitrogen definitely is not happy either, because it has 1, 2, 3, 4, 5, 6, 7. So what do? Well, folks, if a single bond doesn't do it, you do a double bond. So what we're going to do is we're going to move, in this case, atoms, again, between these two, electrons between these 2 atoms. And guess what? Double bond. So if you look at this now, this oxygen should now have 8, 2, 4, 6, 8. This oxygen was already happy to begin with, and now this nitrogen has 2, 4, 6, 8. Everyone is happy. Everyone has fulfilled the octet rule. So again, if there's an extra electrons floating around, look at their electronegativity. Whichever one has the higher electronegativity in this case is going to get the actual electron. Now, something important that comes from the Lewis structure is what we call molecular geometry. And molecular geometry, folks, again, is based upon page 3 of your exam reference sheet. All right. It's called VSEPR geometries. All right. So we're going to talk about VSEPR models pretty soon in lab and in class. So in geometry, all we care, folks, is the central atom, the atom in the middle. And FYI, whether it's a single, double, triple bond, if it's bonded to the same atom, it's considered to be one group. Okay, one bonding group. So I want us to look at this nitrogen atom so far. So right now, this nitrogen atom has 1 bonding group and 2 bonding groups. Okay, so therefore it has, in this case, what we call steric number 2, perhaps. Okay, so it has 2 steric numbers, but it also has a lone pair. Okay, so therefore it has 3 groups around this central atom. So if you go to your VSEPR, in this case model, you should see that in group 3, because there's 3 groups, you should go with number 3, steric number 3, and the second selection from that is actually, it has this 1 lone pair right on top. The geometry of this molecule is called bent or angular. This molecular geometry in the future, folks, and being able to use that page is going to have an implication in the polarity of covalent compounds, which we're going to be talking about next.